today is the last lesson of chapter 11 on area, and we end with geometric probability. So you'll be using segment and area models to find the probability of events. So probability of an event is probably what you have learned in elementary school, middle school. That's where you have the marbles in the hat, the socks in the drawer. It's basically the notation for it is a capital P, and you would write whatever you want in the parentheses. So the probability of getting a red marble, or the probability of getting a blue sock, or whatever the question was about. And you would count the number of favorable outcomes. So favorable outcomes are how many of the thing you need over the total possible. Okay. And all these other probabilities are all the same idea. Here we have geometric probability. This is talking about sets of points as lengths of segments. And again, it's the length of the favorable segment over the total. And probability of areas, which we'll be focusing on, is regions. Okay, so area of the favorable, so what you want, over area of the entire. So essentially the same formula, depending on what you're talking about, has a different name. So this is an example of probability of an event happening. So Main Street intersects each street below. The traffic lights on Main Street follow the cycles shown. As you travel along Main and approach the intersection, what is the probability that the first color is green? So Martin Luther King Boulevard, it says how many seconds each event is. So we want the probability of the first color being green. So the way you denote that is the probability of it being green equals, okay, and on the numerator, you're going to write the time that the light is green over the light it's every other color. Okay. So the probability that it is green, so my favorable is 20 seconds. And in the denominator is the total. So of all the outcomes, we have it being possibly green, possibly yellow, possibly red. So what we do with those numbers is we add them together. So if we simplify this fraction, we get 20 over 75. And then we reduce that. So 5 goes in the bowl. Or 15. So that's as a fraction. As a percent, you type in 4 divided by 15. And what you get in your calculator is 2.6 repeating. So rounding to 1/10 of a percent, this would be 26.7%. And remember, the way you find percents is you multiply that number by 100. Another way to think about that is moving over the decimal point. Okay, same thing here. We're finding the probability of it being green. So what I want is the time of it being green, which is now changed to 25 seconds, over the possible. So it could be green, it could be yellow, or it could be red. So 25 plus 5 plus 45. We simplify that fraction to 25 over 75, which reduces to 1/3. So that's the probability as a fraction. This as a decimal is 0.3 repeating. So as a percent, this is 33.3%. This we're going to skip. We might do this tomorrow, so don't worry about that one. So now on number 3, we're going to find the probability of area. So we have a circle then scratch in a square target with 5 centimeter sides. Find the probability that a dart landing randomly within the square does not land within the circle. I do not want it in the circle, so I want the shaded area, this green. So let's first label it. We have a 5 centimeter sides of a square. Okay, so all the sides are 5. So we'll start with that. So the idea here is I want the probability of the shaded. So I'm just going to break this down over here. So my end goal is to figure out the probability of the shaded. Okay, so what that means is I need to find the area of the shaded because that's what I want. And then on the denominator, I want the total shaded. So area total, that's my goal. So I need to figure out what those two numbers are, just like with the traffic light problem. So what I do first, and this is just me, is I find the area of the whole thing. That's just what I do every single time. So if I'm looking at the area of the total, that's this entire shape. And this shape is a square, so the formula is side squared. And since the side is 5, I'm going to plug 5 into that formula. So the total area is 25 centimeters squared. So that's what's going to go down over here for the area of the total. Now I need to find the area of the shaded, and that usually takes a little more work to do. So to find the area of the shaded, the idea is I'm going to find the area of the whole thing, which I actually already did. And what I'm going to do is I'm going to subtract out the circle. Okay, so that's why we did that shaded area lesson before geometric probability, because this is where it's going to be applied. So I already have the area of the total, so I'm taking the area of the total, and I'm going to subtract the area of the circle. That's my plan. So the area of the total I already got with 825 centimeters squared. I'll write that in there. And I need to subtract the area of a circle. Well, the area of a circle is pi r squared. So I need my radius. So that would be, I don't know, something right here. Well, if you think about it, here's my radius, here's that side. Okay, think of if I were to scoot up the 5, that would be the diameter. So half, which would be the radius, is 2.5 centimeters. So that's what I'm going to plug in. So what I'm going to have to do is get out my calculator and figure out what the pi times 2.5 squared is. So rounding to the 10th, I got 19.6 centimeters squared. So then to find the area of the shaded, I take 25 minus 19.6 to get 5.4 centimeters squared. And that is my shaded area. That's the number that goes here in my formula. So the probability of getting something landing on the shaded area is 5.4 divided by 25, which is 0.216. And you would write this as a percent. So remember, you just move over the decimal point twice, so 21.6% would be the answer to that problem. Okay. Here's a target problem. Part of it's already done for you. So assume that a dart you throw will land on the 1-foot square dartboard and is equally likely to land at any point on the board. Find the probability of hitting each of the blue, yellow, and red regions. The radii of the concentric circles are 1, 2, and 3 inches respectively. Okay. So the first one we're going to find is the probability of getting the blue, which is what it looks like to be the bullseye. Okay, so what they did is if they said it's a 1 foot square dartboard, notice that for the total area, they put side squared, 12 squared, which is 144. And notice that's the same for all of them, because that's the area of the total shape. Okay. Now the hard part is figuring out the area of the shaded. Okay, so to find the area of the shaded, okay, I need to find the area of that bullseye, which they already did. So that's actually really nice. So that's going to be 3.14 inches squared. So if I type that in my calculator, 3.14 divided by 144, what I would get is 0.0218, yada yada. So as a percent, that would be 2.1, actually 2.2%, if I would round, because I moved my decimal point over twice. So that's getting the blue. Now for B, this is where it starts to get a little trickier. You don't have a formula for area of a ring. There is no formula for that. So this is the idea, okay? Find the area of the whole circle, okay? So that you do have, that's this, the 12.56. And what you're going to do is subtract out the middle. And that will give you the ring, that bullseye. So what I'm going to do is I'm going to subtract out the middle one, which is 3.14. So I go 12.56 minus 3.14, I get a 9.42, and then I divide that by 144. And for my probability, I get 0.065416 repeating, yada yada. So as a percent, that would be 6.5% for the ring. Okay, now here's an even larger ring. So, same deal. I'm going to find the area of this whole thing. So this whole thing, so that would be the large one, 28.26. So that's already done. And what I'm going to do is subtract out the middle circle. Oops. So this middle circle. What people get confused on is like, do you need to subtract out the small circle as well? If you took out the small circle as well, it'd be like you have part of your rings missing. So you're only subtracting out that medium circle, so that 12.56. So you're going to go 28.26 minus 12.56, you get 15.7, divided by 144, you get 0.109027, repeating, yada yada. But as a percent, that would be 10.9%. It'll be in the decimal place. Okay, here's dunk tank. Mr. Girardin, of course, sits on a platform above a tank of water. He gets dunked when you throw a ball and hit the red target. What is right? Okay, the radius of the ball is 3.6 centimeters. What is the probability that a ball heading randomly for the given background shape would hit the given target shape? Assume an effective hit is at least half the ball hitting the target. So think about, okay, when you're throwing a ball at the target, it like pushes it back. Now, if I were to hit it like this, say the ball would land there, that would still push it back. Even though it's not like dead center on the target, it would still push it back because most of the ball hit the target. So this 3.6 here that they're talking about, is talking about the radius of the ball, because this would be the furthest the ball could be off the target and still push it down. So that assume an effective hit is at least half the ball hitting the target. Okay. So let's set up our problem here. So we need to find the probability of hitting the target. Okay, so when we write our formula, we need to find the area of the target. That's what we want. And then on the denominator, that's the total area. So like I said, what I do first is I find the total area. And it looks like it's a square target, is what it said. So if this is 40 centimeters as the side, you're going to take 40 and square it. Okay, so I have 1,600 centimeters. So I'm going to plug that in my formula. And then I need to find the area of the target. So again, because the ball doesn't have to land exactly on this, your radius is actually this whole piece here. So the radius that you're plugging in to find the area of the target is pi r squared. And my radius then would be 13.6. So when I do 13.6 squared and then times pi, I get 581.1 centimeters squared. So 581.1 centimeters squared. And then I'm going to type that in my calculator once I have those numbers. And I get 0.363185 is what shows up on my calculator. So as a percent, that would be 36.3% of hitting the target. Last one, find the probability of landing in the shaded region. So probability of landing in the shaded is the area of the shaded over the area of the total. Okay, so area of the total is what I do first. There's no equation for like flower thing or whatever this is, so I'm going to have to be creative. I see that this is a square, so I can use that. So I know that it's going to be I'll do a colon, so this is what I'm going to see. I'm going to find first the area of this square, which is side squared, so that's 4 squared, so 16. So the area of the total is 16 feet squared. And then I have to add in these petals, whatever you want to call them. So let's see, I have 2 semicircles. Okay, well, think about it. If you were to put those together, okay, if you were to put them together, if they're going to cooperate with me here, they make a whole circle. So if I have like 2 sets of semicircles, I have really like 2 circles. So I'm going to find the area of 2 circles. So 2 pi r squareds I need for that one, because there's 2 circles. So now I need the radius. So the radius of one of these circles would be, looks like this would be the radius would be 2. So if I type that in my calculator, I would get 25.1 feet squared for the 2 petals. So the area of the total, I just figured out, was these 2 added together. So 25.1 plus 16 is 41.1. And that's what I would put on the denominator. And then the area of the shaded is what I do next. And then what's shaded are the petals, and I already did that one. So that was this part. So I'm just going to write 25.1. I already did it. So then when I type 25.1 divided by 41.1, what I did as a decimal, I want to write this down a little bit. Okay, what I did as a decimal, 0.61070555, yada. So as a percent, this would be 61.1% when I move over the decimal. And that is it.